All right, welcome to Unit 5 on sampling distributions. In this video, we're going to be taking a look at an example for topic 5.7 over sampling distributions for a sample mean. So hopefully you watch the video on how, all the setup and what all a sampling distribution for a sample mean is, but here is a good example. All right, the amount of time it takes a local fire department to respond to a fire is strongly skewed to the right with a mean of 5.3 minutes and a standard deviation of 2.4 minutes. All right, let's make sure we understand what that means. So it's strongly skewed to the right, which is a good thing, right, if you understand. So that means the mean is somewhere down here at 5.3 minutes to respond to an emergency. And this is good news, right? It should not take very long. It should be very unlikely for it to be very high amount. Most of the time, it should be pretty low, around 5.3 minutes. A very high number would be maybe possible, but would have to, it just doesn't happen very often. That's all good things when it comes to responding to a fire. So the mean for the fire department is 5.3. The standard deviation for any one call could be 2.4 minutes. Again, that understands that any one call is going to deviate. Not every call is going to be 5.3 minutes. All right, what they want us to do is to look at a sample of 40 calls and create a sampling distribution. So what's going to happen when you look at a sample of 40 calls? Well, you're going to get a mean. And you can look at another sample, you're going to get a mean. You're going to look at another sample of 40 calls, you can get a mean. The one thing I know is that all of these possible means, and there's many more than 4, all of these possible sample means are going to vary. Not only are they not going to all be 5.3, they should be close, but they're all going to vary amongst themselves. So let's build a sampling distribution to show me what all of these possible sample means look like. First, let's talk about the center. The center of the distribution should be 5.3 minutes. Why? Well, because that's the truth, right? We know that the mean of all of these means, again, tons of sample means, sample of 40, every sample mean is going to be a little bit different, higher or lower, but the mean of all of those means, as long as they were all randomly selected phone calls, is going to be 5.3 minutes. That makes sense. All right, but we also understand that there's a standard deviation involved, right? All of those means, tons and tons and tons of sample means, all of those different sample means, each of 40 phone calls, is going to vary. And that's where the standard deviation comes in. Now, this is where it's important for you to understand the formula. The formula is sigma divided by the square root of sample size. Now, 2.4 is the standard deviation for one phone call. We're not talking about one phone call. We're talking about the mean of 40 phone calls. So that is why we take the 2.4 and divide it by the square root of 40 to get the standard deviation for the means of 40 phone calls. So all of these different sample means, each of 40 phone calls, are going to deviate. And again, that's the standard deviation comes in of 0.3795 minutes. Much lower. And I got one phone call, that could deviate by 2.4 minutes. Well, guys, we're not talking about one phone call. We're talking about the mean of 40. All right, now we do say that, listen, this formula is easy to use, but it only is applicable if our samples, if we could assume independence between our samples. So as long as our sample size is under 10%, I think it's safe to say that 40 phone calls is under 10% of all phone calls into a fire station. Sorry for the typo here on fire station. There are, if you don't know anything about a fire station, they get lots of phone calls every single day for emergencies of all kinds. All right, so I'm pretty sure 40 phone calls is under 10% of all of them. All right, now the last thing we need is the shape. We really want that shape to be normal, and that's only going to be true if our sample size is bigger than 30. Now remember, the population's skewed right. That's a big problem. But, central limit theorem is like a superhero in to save the day. Since our sample size is big enough, more than 30, central limit theorem says the sampling distribution, not showing you the population, but showing you all possible sample means of 40 phone calls, is going to be normal. All right, so what I did was I put 5.3 in the middle because that's the center as we discussed. I did round the standard deviation for the sampling mean to 0.3, what did I round? It was 0.3795. I rounded it to 0.38. Probably shouldn't have done that, but when you try to fill in one of these models with a bunch of decimals, it tends to get crowded. So I don't mind, if you round to 2 decimals for the sake of the picture, but make sure you understand the standard deviation should be kept in 4 decimal places. So anyway, this shows me, and again on this next slide here, I kind of put it all together so it's all in one place. So we have the center, we got the standard deviation, the spread, and we got the shape here. This shows me that, there's tons and tons and tons of sample means, all of size 40 in this picture. And most of them are going to be pretty close to 5.3 minutes because that's what's true. Some samples could be pretty high and some samples could be pretty low, but that's going to be pretty unlikely. And that's what the normal shape tells me. All right. So now let's use this model. We just spent all this time building it. Let's use it. All right. The National Quality Control Company plans to take a sample of 40 calls. And if the mean response time is 6.5 minutes or longer, the fire station is going to lose money. Why would a fire station lose money? Well, because 6.5 is longer than 5.3, right? And if fire stations are too slow to respond, then, come on, something should be done about it. They should be cut funding, or they should at least be reprimanded or yelled at. Something should be done because they should respond quickly, right? So the question is, what's the probability that the station will lose funding? And should the station be worried about this? So let's take this all in stride. So first off, you're only going to lose funding if the sample comes back more than 6.5 minutes or longer. Now, unfortunately, this normal model cannot calculate 6.5 exactly, so that's why we have to look longer. So I'm finding the probability that a sample mean, X bar, comes back greater than 6.5 minutes. To do that, I need to find the z-score for 6.5 minutes. So I'm going to do 6.5 minus 5.3, and I'm going to divide by the standard deviation, which I found to be 0.3795. Now, every now and then, I'll get some kids who'll say, wait a minute. I thought the standard deviation was 2.4. Go back to the original problem. The standard deviation was 2.4. That was for one phone call. If the question said, what's the probability one phone call comes back more than 6.5 minutes, then I would use 2.4. But the question is asking about a sample of 40 phone calls. That's why I'm using the standard deviation for the sampling distribution that represents what samples of 40 would look like. All right, so the standard deviation, or the mean there, 5.3, take the value, 6.5 minus the mean, divide by standard deviation, using the z-score formula, you should get a z-score of 3.1621. So I'm trying to find the probability that a z-score is greater than 3.1621. Now, to find that probability, I am going to have to go to my calculator, and I am going to have to use normal CDF. I'm going to have to look from 3.1621 to infinity with a mean of 0 and standard deviation of 1. That's for a generic normal model. And if you use your calculator, you get a probability of 0.00078. If you prefer to make that a decimal, that'd be 0.078%. If you prefer to make it a percentage. So again, very unlikely. So the question asks me, what's the probability that they're going to lose funding? The probability that a sample comes back 6.5 or more minutes for a sample of 40, the probability of that happening is well under 1%. So the fire station should not sweat. The fire station should not be worried. I don't think that a sample is going to come back this high. And I will say this, if a sample of 40 phone calls does come back 6.5 minutes or more, then I hate to say it, the fire station does deserve to lose funding, or they do deserve to be reprimanded in some way, because that means they are very slow, longer time to respond to an emergency. And if I live in that community, to me that would be a problem. But for this particular fire station, I don't think they have any major concern, because the probability of such a sample happening would be very unlikely. All right, guys, so pretty good problem to walk through here, pretty easy. I mean, it's so simple. Remember, all you needed to build this model was the mean of 5.3, the standard deviation of 2.4, and the sample size of 40. Then you could find the middle of the sampling distribution. The spread is just following a formula. The shape is just checking that condition. And again, it all comes together. And once it's all laid out in front of you, you could find probabilities all day long. All right, guys, hope you enjoyed this very simple video that talks about sampling distributions for means.